Let's start with today's lecture. The title of this lecture is Analysis of Equilibrium. First of all, let's define the state of equilibrium. The state of rest in an appropriate inertial frame of a system of particles and or rigid bodies is called equilibrium. You may recall that inertial frames are set of observers or reference frames which are with respect to which are at rest with respect to each other, or at most they are in uniform motion along a straight line as seen from each other. So, when a system consisting of particles or particles and rigid bodies or only rigid bodies is at rest in a suitable inertial frame, then we call that the system is in equilibrium. What are the conditions which ensure this state of equilibrium? We will go in a very systematic manner. First of all, we will consider the equilibrium of a particle, a single particle. By definition, particle is a zero dimensional body, that is, it has no length, breadth, thickness, etc., or no diameter. So, it's a geometrically it is a single point. So, when this single point or a particle is subjected to several forces, naturally all the forces must meet at the particle, they are concurrent forces. So, we can say that the conditions of equilibrium of a particle are same as the conditions of equilibrium of concurrent forces. So, suppose F1, F2, F3 up to Fn are force vectors which are passing through the same point as shown over here. This is the location of the particle and all the forces F1, F2, up to Fn are meeting here. Then the resultant force Fr is the vector sum of all these individual forces. This resultant force should be equal to 0 for the state of equilibrium. In the component form, the same condition can be written as the x components of all the forces when summed together they are equal to 0, y components of all the forces summed together gives you 0, and similarly z components summed together is 0. Next, we go to the equilibrium of a single rigid body. Now, the forces are no longer concurrent forces, they may be acting at different points. Suppose here is a anyway, let us say the forces are passing through different points of the body, then the conditions of equilibrium are sum of all these individual forces equal to the resultant force Fr is equal to 0, and besides this we require another set of conditions that the moments of all these applied forces taken about any arbitrary point O is the resultant moment is also equal to 0. Now, suppose I consider the ith force. Let us say here are different forces acting on the body. I choose an arbitrary point O in space. So, the position vectors, if I draw the position vectors of an arbitrary point, let us say on the force F1, F2, etc., the position vectors are vector R1, R2 up to Rn. So, the moments of, let us say, the force F1 about O is R1 crossed with F1. Similarly, for the F2, R2 crossed with F2, etc., up to Rn crossed with Fn. So, these are the first set of terms are the moments of forces about point O. The second set of terms is the moments of couples. Couples are, you may recall, they are free vectors. So, the rigid body may also be subjected to some individual couples. So, the moments of these couples when summed together are given by the second term, that is summation of Ci. So, the resultant moment consisting of moment of forces and moment of couples should be equal to 0. So, for the equilibrium of a rigid body, these two conditions must be simultaneously satisfied. Well, these vector conditions can be easily written in the component form also. For example, sum of all the x components of resultant forces is equal to 0, y components of forces, etc. And similarly, for the resultant moment, the x component or resultant moment is individually 0, y component is individually 0, etc. Well, I have stated that we can choose any point O for taking the moment of forces. Suppose I choose another point O dash. For example, here is point O which was chosen arbitrarily, another point O dash is chosen. Let us select another point O dash. So, now we can join O dash with, let us say, the vector of with force F1. So, this will be vector R dash, and the vector joining O and O dash will be called vector phi. So, it is easy to see that the position vector R I is equal to R I dash plus phi dash, that is the original position vector is equal to the new position vector plus the position vector of O dash with respect to O. So, let us take the moment of all these forces. Let R I crossed with F I is equal to R I dash plus F I crossed with R I dash plus phi crossed with F I, and which simplifies into R I dash crossed with F I plus phi vector crossed with F I. So, taking sum on all these forces, you can easily see that moment of all these forces is equal to the new moment plus phi crossed with the sum of all the forces F, that is summation F I vectors. Now, this is equal to the resultant force, and for conditions of the first condition of equilibrium is that the resultant force is equal to 0. So, it means the second term on the right hand side vanishes, and this leaves us with the interesting result that the sum of moments of all these forces about the new point O dash is equal to the sum of the moment of all these forces about the old point O, and this is equal to 0. So, the consequence is that it is immaterial whether you choose O or O dash or in fact any other point in space. The third stage is the equilibrium of a system of rigid bodies, that is a system consisting of several bodies which are in contact with each other, or they are interconnected through linkages with each other. This leads us to a very interesting concept of free bodies. How do we get the free bodies? Let us consider a system of rigid bodies. Now, we will isolate each individual rigid body from the other bodies, or its subsystem of rigid bodies from the surrounding bodies, and wherever the bodies were in contact with each other, at that point or on those surfaces we will introduce some forces and moments depending upon the type of contact or interconnection, and secondly on this other side of the contact also we will have equal and opposite forces and moments. So, the individual bodies or subsystems of bodies are replaced by suitable reactions on both sides. That's how we will get the free bodies. First we isolate them and then we replace the contacts by suitable actions and reactions. Now, taking each free body as a separate entity, we will now consider the equilibrium, and the conditions of equilibrium are again resultant of all the forces is 0. Secondly, the resultant of all the moments is equal to 0. Let us consider an example to illustrate this point. Suppose the system of rigid bodies consists of a rod which is held by a pin to a wall here, and rod is also connected to the wall with the help of a cord shown here, and then between the wall and the rod there is a heavy disc, spherical or oval disc, which is simultaneously in contact with the wall as well as with the rod. Now, we will break this system into 4 individual bodies. One is the wall as shown here, cord separate, rod separate and disc separate. Now, let us mark down the points of contact. At this point, let us call the contact point as E and D over here. So, there is a point E over here and a corresponding point E over here, point D over here and a corresponding point D over here. Okay. And similarly, for the cord, point C and C, C on wall, C on cord, B on rod, B on cord. Now, one more thing. Now, at all these contact points whichever we have shown, there will be forces and moments. We will see that for different types of contacts, here there is a contact between a flexible cord and a wall. The reactions we will see will be different. For example, cord will be under tension here, which will be an axial force over here. So, there will be equal and opposite force on the wall as well as on the rod. Similarly, here is a pin joint at A. At this point, there can be a force, horizontal force and a vertical force. But on the rod, there will be equal and opposite force. This force is towards right and this force is towards left. This force on the wall is upward, on the rod it will be downward. Okay. Similarly, between wall and the disc depends upon whether the contact is smooth or rough. Let us assume that the contact is very smooth, there is no friction. So, on the wall there will be a compressive force, similarly on the disc there will be also a compressive force and normal to it. Similarly, over here on the between at point D there is a force here. Suppose it is also smooth, then there will be a force, equal and opposite force. So, this is how you will isolate the bodies and replace the contacts with suitable forces and moments. Now, let us summarize about the free bodies. Reactions on two contacting bodies are equal and opposite on account of Newton's third law, we all know about it. Secondly, the type of reactions produced depends upon the nature of contact. As I said, sometimes the contacts are smooth contacts, frictionless contacts, on other time they are rough contacts, that is there is friction. So, each type of contact will have its own reactions. Some so as well as on the surfaces. Finally, sometimes it is necessary to consider internal free bodies such that the contacting surfaces lie within the given body. We will take up this issue later on, because this is not immediately relevant for rigid body mechanics. Now, let us look at various types of supports and connections and the corresponding reactions. Suppose here is a block which is lying on an inclined surface. Now, first of all, we will, as I said, we will consider a smooth contact. In a smooth contact, there is no friction. So, the block is having a weight WA. So, it is due to this gravitational force, it is pressing against the surface, and this action and reaction is normal to the surface, the contacting surface, if there is no friction. So, N up in this direction is the reaction from the surface to the block, and N downward is the reaction from the block onto the surface. When the contact is a rough contact, that is, there is friction between the two, then the reactions are normal reaction N as before, but in addition there will be a force of friction parallel to the contacting surface and equal and opposite force on the surface. So, it means if I take the resultant of two forces F and N on this surface, this resultant will be, you can easily see, this resultant will be passing something like this. Okay. And another type of contact, here is a beam which is resting on a surface with the help of some roller bearings or some ball, or there may be a rod which is pinned with the beam, and this rod itself is resting on rollers which can move on the given surface. Now, it is obvious that through these roller bearings or balls, the vertical forces can be transmitted, but any horizontal force will not be sustained because it will lead to the motion of the beam. So, any force trying to push or pull the beam will be causing only motion. So, it means that there is only one reaction, this is the vertical reaction between the beam and the surface. Suppose the block is being pulled with the help of a flexible taut string or cord. Okay. Then this is schematically shown over here, and if I look at the free body of the block, this string is replaced by a tension along the direction of the string. It cannot sustain any normal component because of flexibility. So, it can have only tensile force on the block, and between the block and the surface normal we will have only the normal reaction if there is smooth contact, otherwise we will have friction also. So, according to the nature of the surface you can choose the reaction. Suppose there is a pin joint or it is supported on a knife edge. So, this is schematic representation. Now, in this case both horizontal and vertical reactions are possible, but no moment is possible. Any moment will lead to the rotation of the beam, which is not sustained. So, for a simple joint or a pin joint, horizontal and vertical reactions are permissible. On the other hand, if the beam is rigidly fixed into the wall, or it is welded to a heavy structure, or it is grouted in a suitable floor or a concrete beam, then three reactions are in general possible: horizontal force, vertical force, and a moment to resist any rotation of the beam. So, 1, 2, 3. All the previous examples were in a plane. Suppose I consider now a three-dimensional contact. That is, there is a rod which is having a ball end and which can move in a suitable socket into the wall or a floor. So, this is called ball and socket joint, just like this. Here is one end of the rod and there is a ball, so it can move. So, in this case, all the three reactions, that is along x axis, y axis and z axis, they are possible, but no rotation can be resisted. So, any moment mx, my or mz will simply lead to the rotation of the ball. It cannot be sustained. Well, I just hinted at internal free body, although we will not be using in this course, but for the completion of the concepts, let us say suppose there is an arbitrary body which is subjected to arbitrary forces, pressure, couple, etc., etc., and I imagine that I have cut the body into two portions, B1 and B2, then due to the molecular forces or atomic forces, each part of the body will be acting on the other part and vice versa. That is, B1 will produce a system of forces on B2, and by Newton's third law, B2 will be producing equal and opposite forces and moments also in general, but here I am showing only the forces. So, B2 will also have equal and opposite forces on B1. So, this is one free body which is individually in equilibrium, and this is the second free body which is also in equilibrium. So, this is an internal free body. The concept of such free bodies is crucial in the mechanics of deformable media such as solids, fluids, etc. Let me illustrate all these concepts with the help of a very simple example. Suppose here is a jar in which three spheres, three balls, steel balls or wooden balls are put. They are in contact. I have enumerated various points of contact. Let us say between sphere A and B, there is a point of contact at 6. Between A and C, there is a point of contact at 3, and so on and so forth. There are different points of contacts. Now, let us separate out the walls and the three spheres. These are the three spheres A, B, C, walls of the jar, and maybe the bottom of the jar also. Okay. So, if I consider the contact point over here, here is a contact point, here is a corresponding contact point, and if this contact is a smooth contact, then A will act on B through a force, and there will be equal and opposite force. Let us say between the wall and the sphere B at point 1, there is a rough contact. What does it mean? That at point 1 there will be a normal reaction and a force of friction, let us say over here, and equal and opposite force, normal reaction and a force of friction downward. So, in this way you can complete all the contacts. For For example, again at point 7 between the ball B and the floor of the jar, here is a contact point and corresponding point over here. So, we will have a vertical force and a force of friction and equal and opposite force. So, this is how you will draw various forces between the contacting bodies. Let us take up another interesting example, a complete system. Suppose here is a triangular frame A, B, C. A is a roller jointed support, whereas C is a simple support, pin jointed or simple support. At point B, the contact between the two rods is through a pin. On the rod AC, there is a pulley through an axle or through a pin at D, and on this pulley is passing a flexible taut cord carrying a weight W. So, here we, for the further analysis of equilibrium, as we will be seeing later, we will first divide this body, this whole system of rods and pulleys and cord, etc., into various free bodies. Let us do it one by one. First of all, we will consider the entire system as a free body, which is isolated from its supports. Supports were at A and C. If you recall, at A there was a roller support and at C there was a simple support. Roller support cannot sustain any horizontal reaction, whereas simple support can sustain both vertical and horizontal reactions. So, here we have replaced these supports by vertical reaction at A, RA, and the horizontal and vertical reactions at C, RC and RC dash. So, this is entire structure as a single free body. Next, we will have, let us say, the rod AB. Now, the rods may be heavy rods, they have their own weight also. So, B is a pin joint, so it means it can have both horizontal and vertical reaction. A we have already seen, there is a normal reaction from the supports as well as the reaction at the pins, because at point A it is connected with the rod AC. Okay. So, besides the reactions, there is a pin reaction at AX and AY, BX and BY. WAB is the gravitational weight of the rod acting through its center of gravity, and T1 is the tension due to the string or the cord. It is a flexible string, so it can have only tensile force. So, T1. When I come to the slant rod BC, again reactions at B are BX and BY, reaction at C are CX and CY. BC, sorry, this is BC, not BAB, WAB, but it should be WBC, vertical downward gravitational weight of the rod BC. Pulley, next is pulley D, again a tension in the string T1, which is equal and opposite to the T1 which was acting on the rod AB. WA is the weight suspended on this other end, free end of the string, and these are the reactions at the pin joint between the pulley and the rod AC, and these are the equal and opposite reactions are dx and dy on the rod AC, and in this way you can at every contact point you must have equal and opposite actions and reactions. So, this is how you will draw the free bodies and the suitable reactions at the connections or contact points. Let us now fix our ideas about the conditions of equilibrium by taking some examples. First, I will take up the example of concurrent forces and then for rigid bodies. So, first example deals with two flexible cables, cables AC and BC. They are contacted to a ceiling like this at point A and B, making angle 30 and 60 degrees respectively to the ceiling, and at the contact point between the two, that is point C, there is a weight of 500 or force of 500 newtons applied. Now, these strings are flexible, so they can sustain only tension, and we are asked to find out the tension in string AC as well as in string BC. Now, all these forces, that is TAC, TBC and 500 Newton force, they are all passing through point C. So, it is a system of concurrent forces, and let us now examine the equilibrium. Well, we have to begin with the problem. First, you draw the coordinate axis x, y, z consistent with the right hand screw system. So, now we can take up the solution both graphically as well as analytically. First of all, analytical solution, the condition of equilibrium for concurrent forces, that the resultant force, which is sum of all the three forces, is equal to 0. So, first of all, we have the vertically downward force, which is minus 500 k unit vector. Then the force in the string BC is resolved into the y and z components, cosine 60 degree in the j direction, sine 60 degree in the k direction, times the magnitude of the force TBC. Similarly, TAC will be in the negative j direction component and a vertical component in the k direction. So, these are the two string forces. Simplifying these components, that is, we will write j component separately and k component separately, we get a single vector equation consisting of the j component and the k component. This vector equation is equivalent to two scalar equations, that is, j component is separately equal to 0, k component is separately equal to 0, and a very simple solution, two algebraic equations for two unknowns we can write down over here, and after substitutions etc., you can get the final result that the tension, magnitude of the tension in the string AC is 250 Newton, and that in the string BC is 250 into root 3 newtons. Okay. This was the analytical solution. Now, we will go to the graphical solution. Well, once again, it is the addition of all the vectors, sum of all the vectors, and by triangle law of vectors, we can show that when the sum is equal to 0, then all the three vectors will enclose a triangle. So, it consists of the 500 Newton force, which is vertically downward, that is the force applied at point C, and these are the two tensions, TAC, which is at 60 degrees and to the vertical, and TBC at 30 degrees to the vertical, or you can say that TAC at 30 degrees to the horizontal and TBC is 60 degrees to the horizontal. So what you do is that, let's say 1 centimeter is equal to 100 newtons, so you draw a 5 centimeter line at the 2 points of this straight line. You draw one line at 60 degrees to the vertical and the other at 30 degrees to the vertical. Wherever they intersect, that will be the apex of the triangle, and then to find out the lengths of these two sides, you use sine law of triangles. So TAC divided by the sine of the angle opposite to this side, that is 30 degrees, equal to the vertical 500 newtons divided by the sine of this angle is incidentally 90 degrees. So sine 90 degrees, and then similarly TBC divided by the opposite angle sine 60 degrees. So simplifying, you will get the same result as the analytical solution provides. Now we come to the analysis of equilibrium of a system of rigid bodies. That is, suppose we are given a system consisting of more than one rigid bodies which are in contact, or they are being supported by walls or floor or some other interconnections, etc. Then first of all we will consider the entire system as separated from the walls or supports as a single rigid body, and then we will see that how many reactions are to be found out. In the case of a plane system, that is when all the bodies are in the same plane, forces are also in the same plane, then naturally we will have three equations of equilibrium: sigma fx is equal to 0, sigma fy is equal to 0, and sigma mz, that is the moment about z axis, equal to 0. But in the three-dimensional case, we will have 6 equations of equilibrium: sigma fx is equal to 0, sigma fy is equal to 0, sigma fz is equal to 0, that is for forces, and similarly sigma mx is equal to 0 taken about any arbitrary point, sigma my is equal to 0, and sigma mz. So if your reactions are let us say only 3 reactions to be determined for the plane case, then the 3 equations of equilibrium and the system we can solve. If there are only 6 reactions for the 3D case to be found out, again we can solve. But in some cases there will be the equations of equilibrium are not just sufficient to solve for all the reactions. Then we will have to, if the number of unknowns equals the number of unknown reactions equals the number of unknown, I think we should say that if the number of unknown reactions is equal to the number of equations of equilibrium, then we will solve the problem. If not, then we will have to consider further free bodies. That is, we will break the entire system into separate free bodies or subsystem, and for each we will write down the appropriate equations of equilibrium. We will come to a state where the number of total unknowns is equal to the total number of equations. Then the problem is solved, and we call the problem as statically determinate problem. If the number of unknowns is greater than the number of available equations of equilibrium, then the problem is indeterminate. Let us take the following example. Solve for the supporting reactions at A and C for a structure loaded as shown here. It is given that the rods AB and BC weigh respectively 1000 newtons and 1500 newtons. That is, let me explain the problem. Here are two rods, they are pin jointed at point B. At point A, the top rod is pin jointed to the wall, or there is a pin connection, and similarly at point C there is a pin connection. There are two strings attached to the rod BC, and these two strings themselves are simultaneously carrying the weight of 2000 newtons at the point D. The distances are given 0.6 meters, 0.2 meters, and this angle is 30 degrees. The distance between A and C is 1 meter. So, we have to find out the supporting reactions, that is reactions at A and C. So, this is a pin joint, this is also a pin joint. So, two reactions here, two reactions here. It means you have 4 reactions. So, normally we will require 4 equations to solve for 4 unknown reactions. But in the plane of the body, all the forces and the structure is in single plane, only 3 equations of equilibrium are available. So, it means we have to do much more than that. First of all, we will write down the equations of equilibrium for the entire structure separated from the wall, taken as a single free body. Sigma Fx is equal to 0. So, let me say that here is Ax, x is the horizontal reaction, Ax, then Ay, similarly Cx and Cy. So, you can say that Ax plus Cx is equal to 0, sum of vertical forces is 0, means Ay plus Cy is equal to the sum of applied vertical forces. 1000 Newton plus 1500 Newton, these are the weights of the two rods, and this is the applied force in the vertical direction at point D. So, the total vertical force, again looking here, this is 2000, this is 1500, this is 1000. So, the total vertical force is 4500. And then you take moments about any arbitrary point of all the forces. Now, which point should I take? Well, let us take the moments about point C. Okay. So, if I take moments about point C, the Ay component is passing through C, no moment will be produced by it. So, there will be moment due to Ax and the vertical force here, vertical force here, vertical force here. So, these 3 forces will produce moments, and the horizontal force at A or horizontal reaction at A, that will produce moment. So, these are the 2 terms which are producing moments, and that solves for Ax is equal to minus 3365 Newton. Now, the significance of this minus is that we had taken Ax as pointing towards the right. So, since the answer is negative, it means in fact it is pointing towards left. So, the upshot is that you can choose any reaction in the appropriate direction, but sense can be arbitrary. If the answer comes out to be negative, it means the actual force is in the opposite sense. So, once we have this, then using the first equation we can find out Cx, which is equal to minus Ax, which is 3365 newtons. So, this is positive, it means the chosen direction is the correct direction. Now, to solve for the other 2 unknowns Ay and Cy, we cannot solve from the previous 3 equations, as the number of equations is less than the number of unknowns. So, let us take one extra free body. Free body we are taking is the rod AB. So, in the rod AB we have already determined that 3365 is the reaction in the horizontal direction, and this is the force 1000 newtons, the length is 2 meters, and the unknown reactions are AY, BX, BY. So, total unknowns are 3, and the equations available in the plane for equilibrium are also 3. It means we will be able to solve the problem. Well, equations of equilibrium for the free body number 2, again sum of horizontal forces is 0, sum of vertical forces is equal to 0, and now we will take moments about B. Well, 2, because we have chosen B because 2 unknowns Bx and By pass through B, and hence their moments is 0. So, I will immediately get Ay. So, finally, collecting all the results, we have Cx is equal to minus Ax is equal to 3365 newtons, and Cy is equal to 4500 minus Ay, that is 269 newtons. Now, let us go to one very important concept, namely the concept of two force members. Sometimes there is a rigid body which we are told is subject to only two forces and the body is in equilibrium. As we will be seeing in the next lecture, when we deal with structural mechanics, the truss problems, those members or elements of a truss, they are good examples of two force members, because two forces are acting on the ends of the members through pin joints. So, the direction of the forces can be arbitrary direction, as I have drawn here. So, at point 1 and point 2 there is F1 and F2. Okay. Now, the member is in equilibrium, this body is in equilibrium. So, by conditions of equilibrium, the sum of the two forces F1 and F2 is equal to 0. So, what does it mean? That F1 is equal to minus F2. So, in other words, this body is subjected to two equal and opposite forces, that is, it is subjected to a couple. Now, the couple will produce a moment. Let us say the moment is C, vector C. The condition of equilibrium for the rigid body is that C should also be equal to 0, otherwise the body will start rotating, it will no longer be in equilibrium. So, it means to fulfill that condition, the moment of the couple should be equal to 0, that is, the two forces should be collinear forces. So, whenever a rigid body is subjected to two forces and the body is in equilibrium, at best it can be subjected to two collinear forces. Okay? There cannot be any other possibility, and accordingly, if the two forces are both pointing into the body, as shown over here, F1 and F2, that is, they are going into the body, then we call the body or the member as under compression. Whereas, if the two forces are going outward from the body, as shown over here, then the member is said to be under tension. Here I have drawn the body as if the forces are along the body itself. The body can be of any shape, for example, an angle shaped or a curved body, and let us say the two forces are passing through these two pins. then for sure the pins will be joined by a line, and the forces will be acting along this line. Similarly, if the member is a curved member, then it will be again passing through these two pins which are along the same line of action. So, these two simple conclusions are very, very useful in the analysis of trusses. Now, let us look into another concept which I have already hinted to some extent: statical indeterminacy. When the number of unknowns is larger than the number of available equations, then we cannot solve for all the forces and moments required to maintain the body in equilibrium. Some other concepts like deformations or other things, they are required for solving the problem. In that case, the structure is called statically indeterminate structure. Many civil structures are statically indeterminate structure. For us, a simple case will be, suppose there is a beam or a bar which is pin jointed at the two ends into the two supports, and then the number of reactions will be 2 reactions at this end and 2 reactions at this end. It may be subjected to a vertical force, a horizontal force, a moment, etc. Well, this structure cannot be solved with the help of the equations of equilibrium alone, and hence this structure is statically indeterminate structure. Another possibility is a beam which is fixed into the wall, that is, it is grouted into the wall as shown over here, and on the other end it is also supported on a roller end, a roller support. Then we have said that there are 3 reactions at this end, at a fixed end: vertical reaction, horizontal reaction, and a moment reaction. So, 3 over here and 1 reaction from here. So, the total number of reactions is 4 reactions. Number of available equations of equilibrium are 3. Again, we have a indeterminate problem. Well, so in this chapter or in this lecture, we have seen how to analyze the equilibrium of either a single particle or a single rigid body or a system of rigid bodies which are interconnected with each other. And the crucial aspect of this analysis is that if you are given a system of rigid bodies which are in contact or interconnected with each other, then how to choose appropriate free bodies, because the choice of free bodies will determine how easily or how quickly you can solve the problem. And once you have chosen the free bodies, it is equally important to replace the contact points through a system of reactions. Reactions may be force reactions or moment reactions, and what are their directions, whether it is a pin joint, roller joint, or a flexible string connection, etc. Okay? And then for more complex problems, we should first examine whether the problem is statically determinate or indeterminate. In this course, we will be almost always be concerned with determinate problem, statically determinate problem. And once important application of these concepts will come in the next lecture, namely when we will take up structural mechanics. So, till then we will see how to use this concept, and I thank you for attention for today's lecture.